Hi. So let's recap the question a little. I point to two stones, stone one and two, and the wizard tells me um, stone three is the sum. Correct? Given all this, I want to find um, what is the product of, say, stone two and stone three. So I have this great giant multiplication table with all possible combinations and it somehow stores everything. And from that, I want to like find out, given two stones, he tells us addition, what can be the multiplication. So what we can do is we can try to find stone with the value equals to. And how will we do this? Say there are n stones, right? Um, There are n stones. We will search all over for a stone X such that the stone X cannot be written as stone Y, stone Z. And this simply follows that from the fact that for all natural numbers, you can write them as a sum of natural numbers, positive natural numbers, numbers greater than zero. Uh, so you can write them as a sum of the natural numbers except for one. One, you cannot really go to anything less than one. So that. So once we have found this stone x, we can actually use it to reconstruct the values of the some arbitrary stones we have. And these numbers are arbitrary, like they're not representing the value or anything. So how do we do this? So let's try to do it from an example. Um, so what we can do is we can say, what is stone x plus stone x? What stone does that give us? Whatever that is, whatever this is, stone, whatever it is, will give us the stone corresponding to the value of 2. Correct? So now, now that we've got this, we've got the stone corresponding to the value of 2. We can get to 3. And how do we do that? We say, we do the same thing we did before. We say stone x plus stone 2, so stone 2, will give us some stone 3, and this has the value of 3. So we keep doing this until we find the values of these stones. And again, noting these are arbitrary. Actually, these things with the actual values are put an underscore. So these are just arbitrary. Anyway, until we get the value of these random stones, we can just continue doing that. And yeah, so after we do that, we can get the values and then we can just multiply them out as I've written here. Then, and the main point of this was that you can literally write any natural number that is an integer greater than 1 as a sum of two natural numbers. So once we found one, our work is basically easy. So let's go to question 2 and try to do what we did again with question 1. Can we find the stone with value equals 1? We can, right? We can do that. So imagine going through for stone y times stone z. Uh, we point at these two stones, and the wizard points back at stone y for every stone. Then the stone z is the stone with the value of 1. But like, okay, so that's a good thing. We've got this one with the value of 1. And now how can we recover anything from it? So how can we get, so 2 times 1 would point to 2. So we cannot really get somewhere, right? Or 2 times 2 would point to 4. So we can get like, oh, okay, pointing at the same stone twice gives you the squared stone. So, but we can't really find the value of this. And let's just illustrate like, suppose we have a composite number that can be written as like 1, again arbitrary, times prime 2, times prime 3. Now we have all this. It can also be written as say some composite 2 times prime 3, maybe we can write that like that. So we can track these primes. We can track which primes track to which composite, right? Because composites can be written in 2 ways like this, but primes can only be written as one, like prime is equal to 1 times the prime. And that is the only place this prime will appear. It will not appear as like the wizard won't point to the prime for any other choice, right? Only when you're pointing to the one stone and to the prime itself. So we can track down these primes. We can track which prime stones correspond to which composite stones and all that. But it's just hard to get the value of the prime. And we don't have that, then it's hard to tell us what the addition of 2 random stones would be. Alright. So I don't think this is possible. Not possible. So that's what I think. But let's think about something else maybe. Yeah. I'm not going to do Q3 because I'm kind of out of time. So I'm not going to do Q3, but I might cover it in another video. So for Q4, I think by symmetry, what this was trying to hint at is that um in the addition case, you could like add by 1. You could like add by 1, increment by 1, and see the difference. So, like, but for the multiplication case, like these primes, any way you order them, it doesn't change the result. In fact, even like if you have like a multiplication table, and if I put like something like 1, 2, 3, 4, this way, then if I reorder these 2 rows, I think that still won't change the result here. Like, let me. So like there's like a lot of like yeah, there's like a lot of like I don't know about the table. I think I'll have to relook into that. But ignore the table for the time being. But so like yeah, I think what Kashipur is trying to say is that the symmetry is more ambiguous and we cannot figure stuff out because of that. I'll revisit that after I do question 3. So yeah, this was about it. Mm, right.